What's up, YouTubers? So today is the day. We are going to test 70-24 rods on 3/8 plate, and we're going to bend it towards the face and away from the face on a fillet weld and see what happens. If it's stronger than 70-18, if it's as strong as 70-18. We don't know unless we test it, so let's get into it. So I've released a bunch of test videos recently on different stick rods, MIG, and etc. You get the picture. And I've learned a lot of things in the testing, and that's sometimes things don't go as you expected, especially when it comes to breaking welds. Now, there's so much more to go in depth than what I've done so far, and I've read tons of comments, and your comments are great because you bring up tons of stuff that I didn't think of and possible holes and theories that I have and all of that. And that's how we all learn, is by, well, making mistakes and retrying and trying to be as close to scientific as we can on it so we can get repeatable results. Well, that has led us to today's video, or today's topic, which is 70-24 rods, and we're going to brake test it to see what happens. Now, in the previous test videos, 70-18 has passed on a bend away from the face, so a tensile strength test. ER70 MIG has. However, 70-14 rod did not. 60-10, 60-11, 60-13, all of those have failed on bend tests away from the face. So by testing 70-24 today, we're going to see if that also indeed fails when bent away from the face of a weld. The particular rod I'm going to be using today is Blue Demon 70-24. I generally run Lincoln's Jet Rod, which is what they call their 70-24. So I have ran this rod before, runs decent. I do like Lincoln's better, and it is 1/8" rod. And for those who don't know, because you can't just buy this off the shelf at your local Tractor Supply, this rod is ran in a flat position only, and I guess horizontal as well, but you cannot run it uphill or vertical. The molten puddle's so liquid, it's like running water. So it would run and just melt off on the floor, so you don't want that. But this rod is very, very big for an 1/8" rod because of how much flux is on here. This flux contains iron powder. That iron powder turns into part of the weld deposit, and that's why you get very high travel speeds with this, very high deposition rates, which is kind of why they call it jet rod. You know, get stuff done. Commonly used on trailers, on tanks, or anything like, I don't know, ships where you have a butt weld that you just need to weld down. Great rod for that, especially in bigger than 1/8" sizes. But it produces a very wide weld, very high deposition, like I said. Now, this is not a low hydrogen rod. Therefore, this is not code legal to use on anything that specifies low hydrogen, and you would not want to weld high strength steel with this. So any kind of AR500, AR400, or stuff you might find on a tractor that's wear resistant, and even in theory, really thick steel may be susceptible to hydrogen embrittlement. And I'll put a video link down in the description if you want to learn more about that, but you don't want to run this rod for that. So non-critical work is a good overview of that. So with that said, I'm going to get these assembled up and weld all of them in the flat position. I am not going to do a fillet weld, and that's simply to reduce the possibility of a mistake or undercut being made because of how liquid this puddle is, and I don't have that much steel ready for today, and I can't afford mistakes. So we're going to weld it in a flat position. Let's get into it. So I got all of these welded up, and guess what? Mistakes were made. So the first one that I welded had a difficult time starting the rod, and that's because the flux on this is so wide, trying to strike it down in the corner was almost impossible because the rod tip never contacted the metal. So like an idiot, I tried to strike it a little bit higher and bring it down. Well, I had a bad start, and look, arc strike. That's generally an undesirable characteristic. When you have an arc strike up above where you weld, that can basically, as this gets bent, it can create a spot for a crack or a tear to propagate from. And it also, depending on the steel, will harden that area, which is undesirable. So this one, it's still acceptable for what we're going to do, but it's not perfect. This one I am going to bend towards the face because that arc strike will be less of a concern then. This guy, which is basically perfect, corner isn't too blown out. I mean, it has a little bit of a divot there, but it's not any different than any other test I've done, so I don't really see that as a negative. The start's nice and hot. It wrapped the corner pretty good. Very shiny weld, very acceptable. There is not one hint of undercut or any other weld defect in the meat of that, so that all looks good. This we are going to press in the shop press and try and flatten out and see if it passes. Now this guy, I learned a valuable lesson that I often forget. Even though this was clamped when I welded it, as soon as I was done welding it, I unclamped it, sat it on here, and as that weld cooled, look how much that pulled. Pretty wild. And as part of this test, I don't tack anything. Had I tacked this and kept it clamped a little bit longer, this would have never happened. But this rod, due to the metal deposition rate, has a really bad tendency of shrinking a fair amount, and guess what? That will pull things. So this one, I think we're gonna press it in a shop press, but the odds of a failure, I would say, is higher because it's gonna have to stretch that weld a lot more as it closes that gap. But that's what we got, so let's start out with breaking this guy with the arc strike towards the face. All right, so got everything set up to break this weld towards the face. Now I'm going to make a prediction, and I'm probably going to be wrong since I'm wrong a lot in these videos. I have a feeling this is actually going to outperform 70-18, and it will probably outperform 60-10. And the reason I say that is I've done cut and etches on this 1/8 inch 70-24, and it seems to penetrate really good, like shockingly good. Part of it is the amperage. I mean, 150 amps, I think, is what I welded this at. That's a tremendous amount of heat put in. But I've ran 70-18 at 150 amps for an 1/8 inch rod, and it does not penetrate as much as this rod does at 150. So my guess is it's going to break above 90. The weld itself really isn't that big. It's not like massively oversized. It's about the same size as a 70-18, maybe a smidge bigger. It is, I would say, on par with a ER70 MIG. So nothing too crazy. All right, we're zeroed out. Let's break this. Oh, look at that. I was wrong. Well, of course, it cut out. It was 71 something. So not as strong as I thought. See? Told you I was going to be wrong. So I got this guy set up. We're going to bend / break the one that's tilted a little bit. Weld-wise, it looks really good. It's flat. There's no undercut. It's at a proper 45-degree angle, so really nothing too much to write home about there. The end's a little bit blown out, as are most of these, and that's why, to really be fair, I should cut the section out of a middle part of a plate that doesn't have a start or a stop. That way it's more consistent, but this is a more realistic example of something you might weld. And to fix that, you would simply wire wheel this off like I did, or clean it up and then restart and then fill that in. You could weld it from the corner in or whatever, but we're going to leave it there and see what happens. I've left it for every rod thus far. Some have passed, some haven't. It's going to be a little bit difficult to bend this because of the angle, so it might take a few shots. All right, let's bend this. All right, I'm going to let up the pressure a little bit and reposition this now that it's straight. There we go. I can already tell this thing isn't going to want to give up much. Oh, and we have a failure. Yep. All right. Let's bend the other one and see what happens. This guy has very little, if no, weld defects at all. The end isn't even really blown out that much. Man, this one is taking some force. Bang! I had a feeling that was going to happen. All right, let's go to the welding bench and look at these. Well, that last one, that was quite a failure. Literally blew apart, so you always want to be careful and use your safety squints on that. So what I'm going to do is I'm going to break this, or the rest of the way. This was the bend towards the face, and we're going to start by looking at that. So when we look at this guy, and let me zoom in for you, we have some penetration. The first part of the weld, pretty cold as expected. I had a rough start. Settled in, we had some penetration, and then near the end tapered out and virtually no penetration. So this was the bend towards the face. This is, I would say, typical results. This really doesn't look that much different than 70-18 and not really a whole lot different from, I guess, 70-14. Now the test results of this put it right at, I would say, the low end, maybe a little bit under what 70-18 would normally perform in this test with my test equipment. So it's not as strong. I had made a prediction. I thought it was going to be up in the 90, maybe 100, and it wasn't. So the root cause of that is the penetration isn't quite as good as what I would have expected, but it did get in there, and the results, I would say, are on par with 70-18. Believe it or not, ER70 MIG actually does exceptionally well on this, on a 200 amp MIG welder on this 3/8 plate. It actually surpasses the strength of this rod and 70-18 on a bend towards the face. So pretty interesting. Now, what's even more interesting is how these other ones failed. And let me zoom out. So for the two bends away from the face, so let's look at this guy first. This failed at a lower pressure reading, didn't grenade pretty much, which was good. By the look of it, it tore some of the plate out here in the middle, not a whole lot of it. And the weld appears to have broken itself at the end and at the start. So the weld failed through the weld, not the plate. Not too unexpected of results. This one is far more interesting. I looked over this pretty closely, and this is basically more or less about as good as you can get on this without going back and restarting and filling this in. Again, the weld cracked over here a little bit and then propagated up. But when you actually look at this, the whole weld actually failed itself. When you look, there's no penetration there. Let me zoom in. The plate edge is virtually untouched, and it failed. It didn't peel off any of the plate, only the weld remains. So the weld itself was not as strong as the plate in this case. So this is a common result when you bend it this way towards the face, but bending it away, I have not seen on any test where the weld itself broke. Pretty interesting there. Now let's compare and contrast the 7014 and 7018. All right, so let's compare these. These are 7024, got a 7018, 7014, 7014. Let's just compare these two. So the 7014, I've done at least, I think, 6 of these now. They all break in the same manner roughly, which is they tear out a big chunk out of the plate. The crack may start down here in the corner where the weld is the thinnest and then propagates, but realistically, that's how all of these welds will likely do, but tears out the plate. The 7024, in this case, the weld itself failed and none of the base material was pulled out. This one right here, about the first third, last third tore out where the weld failed, and then it took a chunk of the material in the middle, but a little bit different. Pretty interesting results. Now, the 7014 tends to tear right at, and I don't leave too much of a fisheye there, but there is a little bit of one. This one was filled in far better, and all that happens is the crack starts and it breaks up top of it rather than down here and then up. I don't honestly think it would make much of a difference if that was completely filled in or overfilled. It's still going to break on the top toe line because of how this is stressed. And to contrast it to the 7018, I've done, I don't know, 3 or 4 or 5 of these on camera, and I've done at least, I don't know, 8 or 9 more of these off camera just for random things, and I have yet to have a 7018 fail, okay? And you can see how much more this is bent back, and I even put enough pressure to bend these two together. I mean, you were talking over 9 tons, and this weld still did not fail. It even has a start of a crack or a crease there where it's pulling against it, but it has not given up. These guys here, like I said, even if I didn't have that little bit of a underfill there, it still would have failed and it still would not have held together like this did. So realistically, I would say 7024 is not as strong as 7018. Now, is it as strong as 7014? I would argue and say that it's in the ballpark, but probably a little bit stronger. And the reason I say that is because in the bend towards the face, saw much better numbers with this 7024 than with the 7014. But I would say these two are closer to being equal than any of them are close to being 7018. And let me show you something else. What kind of amazes me is this is a 7018 weld. I have virtually no weld deposit here, like I screwed up and, you know, no weld there, very minimal thickness. The end of this is, I would say, blown out as bad, if not more, than the 7024 rods. I mean, look how thin that is there. Very thin in that section on both of them. And this still didn't fail, nor has any of them. And then when you look at how thick like this is, I mean, that's easily twice as thick. And look at the start. I mean, just compare these two. You know, no metal, bunch of metal. So from a strength perspective, you know, and even now that I look at this, I would argue that the 7018 weld is actually smaller than the 7014 weld. Yeah, I would definitely say it's shorter leg height. Interesting. All right, let's go to conclusion. Well, what did we learn today? Well, I learned that there's quite a difference between your 70 series rods, and they don't all perform the same. You know, and it goes without saying that you can't just judge a book by the cover, as much as I hate saying that. Every rod has different performance characteristics. From my perspective, I would say the 70-24 under max load seems to be more brittle. And we saw that where it just catastrophically failed. And by the way I can tell when I'm putting pressure on it in the shop press, it seems like it doesn't give a whole lot of warning and then it fails. It's not quite as bad as like gasless flux core. That's probably the worst that I've experienced for pressure versus up until failure. But it definitely does not perform, I guess, as good as 70-18. And I hate to keep talking about 70-18 and bringing this in, but the performance is not as good. There could be, at least in my theory at this point, doing all this testing, two possible reasons for that. One, hydrogen embrittlement. I did a lot of research on this, and A36 hot rolled, which is what this plate is not known to be susceptible to hydrogen embrittlement. However, caveat, on thicker plate, half-inch and thicker, hydrogen can play a role in ultimate strength from what I've read. This is close enough, being 3/8, to where the effects that hydrogen may play in this may be enough to cause failure. So that's a possibility. The other possibility is that the 70-24 that I ran in this video simply does not have anywhere near the strength of the 70-18. And what I mean by that, this 70-24 is made by Blue Demon, okay? When I look up the specs for a Blue Demon rod like the 70-24, they list American Welding Society minimum specs as the spec for that rod. That means that it has to be 60,000 for yield strength and 70,000 for tensile strength. Now, it's very common for rods, for all welding electrodes and wire, to test much higher than the minimum, because remember, that's a minimum spec. Well, Blue Demon doesn't tell you what their rods actually tests at. I can find what this is tested at, and I can find what the 70-14 tests at. Well, it's entirely possible that tests within like 1% of what spec is, which could coincide with why it could not take the load of like 70-18. So that is a possibility. I mean, Blue Demon doesn't test it. The only real way to find out if that was the case is to test a rod that has known test specifications, like say Jet Rod from Lincoln, where they actually published the typical results of it. And that might be a more fair comparison. However, realistically, I don't think it's going to pass. And based on all the previous testing I've done on this, I'm starting to suspect that hydrogen embrittlement might be the root cause of why all the 70 series rods are failing and 70-18 is not, and ER70 MIG is not, and Dual Shield did not, even though the Dual Shield I haven't put on film yet. I did test a simple test, and it had no issue passing on a bend test away from the face. Now, the one thing I do like about the 70-24 is that on a bend towards the face, which was it this guy? No, this guy right here. It broke at close to, I would say, in the ballpark of 70-18. So that's really good. It seems to have more penetration than 70-14 does, and that coincides with past testing I've done on flat plate that showed, and even fillet welds, 70-14 tends to have the least amount of penetration of all the rods I've tested, along with 60-13. So from a standpoint, would I use 70-24 instead of 70-14? Based on my testing in the flat position or on a fillet weld, I probably would use 70-24 over 70-14. The primary reason being, I know that if I can only weld one side of a fillet weld, that this will perform better than 70-14 will when it comes to stress towards the face. And then away from the face, it seemed to take a little bit more pressure than 7014 did as well. So yeah, in a flat position in fillet weld, I would have no problem running 7024 over 7014. Now, the big limiting factor on that is 7014, you can run uphill and overhead. You cannot do that with 7024, so you're more limited on what you can really use this rod for. So it's all things to consider. And again, this is, you know, kind of a conglomeration of a bunch of other tests here thrown in here that isn't what we actually tested in this video, but I wanted to share that because this is important knowledge if you need to make decisions on what rod to use. But yeah, with that said, I do personally like 7024. I like the way it runs. I like the bead profile. It looks like chrome when you get a good run with it. So yeah, I like it, but is it great for all situations? Absolutely not. And realistically, is it a substitute for 7018? I would say on a flat position, filling gouges in something, absolutely, but to actually weld something for strength, definitely not. 7018 is the way to go, 100% in my opinion, and all the testing that I've done seems to point that way as well. But this won't be the end-all, be-all testing on this. I will be going back in and trying to eliminate some more variables to really determine what's going on here. If it's just a raw strength perspective, if it's a hydrogen embrittlement issue, etc. So there's a pretty deep rabbit hole to go down in this situation to figure out what's going on. With that said, if you got any comments, questions, thoughts, concerns, you know where to leave them. Appreciate you sticking around for the video. Until next time.